Let's check whether the given set G with elements 1, 2, 3, 4, 5, and 6 is a group under multiplication modulo 7. We have here our Cayley table. We need to complete this first before identification of the axioms. But of course, in the identification of whether this set is a group or not, we start with the idea that obviously our set G with components 1, 2, 3, 4, 5, and 6 is obviously non-empty. And with that, let us try to identify whether the given operation is closed so that we can really determine that the operation is a binary operation. So let's define, let's star B multiplication modulo 7, so that we can invoke the use of star later on as we have defined it already. So since we now define star as multiplication modulo 7 to identify whether the given operation is closed under that star, let's try to complete the Cayley table and take note that our operation is modulo 7 or multiplication modulo 7 more specifically. We're going to multiply the selected elements and then take its quotient when divided by 7. So the Cayley table is here for that matter. Let's start with 1 times 1. So 1 star 1 or 1 times 1 in terms of modulo 7 is just equal to 1 modulo 7. 1 times 2 is also 2 modulo 7. 1 times 3 is a 3. 1 times 4 is 4. 1 times 5 is 5 modulo 7. And 1 times 6 is 6 modulo 7. So that's very easy because we have 1 as our one of our factors. Next, for the second row is 2. 2 star 1 is actually 2 modulo 7 is still 2. 2 times 2 is 4. Okay, take note, 2 times 2 is 4. We are multiplying, not adding. So 2 times 2 is still 4. Still 4 modulo 7. 2 times 3 is 6 modulo 7. Now here comes 2 times 4. 2 times 4 is 8. So 8 modulo 7, when divided by 7, you still have a remainder of 1. 2 times 5 is 10. Modulo 7 is actually 3. 2 times 6 is 12. Under modulo 7 is 5. So as of this point, we can still see that the elements or the results when we operate those elements are still under set G. We still have 1, 2, 3, 4, 5, 6 as our results. Next, 3 times 1 is 3. 3 times 2 is 6, modulo 7. 3 times 3 is 9, so modulo 7, that's actually 2. 3 times 4 is 12, modulo 7, you have actually 5. Then 3 times 3 times 5 is 15. So 15 modulo 7, actually we have 14, right? Multiple of 7, so you have 1. And 3 times 6 is 18, modulo 7 is actually 4. Okay? So to continue, 4 times 1 is 4 modulo 7. 4 times 2 is 8, so that's 1 modulo 7. 4 times 3 is 12, so again that's 5 modulo 7. Next is 4 times 4 is 16, so that's 2 modulo 7. 4 times 5 is 20, so modulo 7, that's actually 14, so you have 6. And 4 times 6 is 24, modulo 7, that's 21, the closest multiple of 7. So 24, 21, you have a remainder of 3. Now some of us might think that what if we're going to draw a diagonal here and simply reflect the results, because we might see here 1, 2, 3, 4, similar 1, 2, 3, 4, 2, 4, 6, 1, 2, 4, 6, 1. Some of us might try to guess that. Yes, you may do that, and as long as you have identified that the operation is actually commutative. Since here, we don't know, or we haven't seen any claim that the operation is commutative, so we cannot do that, even if it will look like commutativity later on. So just simply continue. 5 times 1 is 5 modulo 7. 5 times 2 is 10, that's a 3 modulo 7. 5 times 3 is 15, so 1 modulo 7. 5 times 4 is 20, that's 6 modulo 7. 5 times 5 is 25 modulo 7, again 21, so that's 4. 5 times 6 is 30 modulo 7, that's 28, so we have 2. Next, 6 times 1 is 6 modulo 7. 6 times 2 is 12. That's actually 5 modulo 7. 6 times 3 is actually 18. So modulo 7, that's actually 4. 6 times 4 is 24. So that's 3 modulo 7. 6 times 5 is 30. So modulo 7 is 2. 28, right? 6 times 6 is 36. The closest multiple of 7 is 35, so you have 1 modulo 7. Again, even if you're going to draw it here and you would see actually just reflections along the diagonal line, it doesn't work that way all the time. So it's okay to do it like this. Now, the purpose of the scaling table, as mentioned, is to identify the closure property. And as you can see, all the results here are just elements 1, 2, 3, 5, and 6 rearranged depending on the result. So we have here 1, 2, 3, 4, 5, and 6 are all element of G. Then we can say that our star is closed, or G, yes, G is closed, sorry, that's closed under the operation star. So now that we are done with the closure property, and at the same time the Keeley table to be used later on for the rest of the situation, let's proceed now to the axioms. There are 3 axioms for a group or a set to be called a group. The first one is whether star is associative in G. To determine associativity, just like the usual associative property in usual multiplication, even in addition, we need 3 elements and determine whether the results from different groupings will be the same for whatever grouping you used. But this time, since our operation is at the usual multiplication, we have multiplication modulo 5, we can actually just invoke the possibility that since the elements of G 1, 2, 3, 4, 5, 6 are also elements of the integers, and multiplication is in general associative in the set of integers, so we can use that in this perspective. Some references invoke that immediately. This time I will try to make some scribbles here of mine, and probably this might not be acceptable for all, but I'm going to provide a certain discussion on the associativity here. So we have here, since multiplication is associative in Z in general. Okay, I'm talking about Z in the meantime, and 1, 2, 3, 4, 5, 6 are also element of Z. They are all element of Z. Then, just for the usual multiplication alone, we can guarantee that A, or then we say that when we group AB times C is just equal to A with the times the grouping of B and C. That is for the usual multiplication. Okay, so since they are all elements of Z. Now, this is also true for all A, B, and C element of G, because all elements of G are elements of Z as well. So what can we draw to this once we are sure that since usual multiplication is associativity in connection to our operation in the next part? So we can say here that since, if we are going to assume, since if A times B times C is, say for example, congruent to D modulo 7, okay? So whatever be the result of that, if it's under modulo 7, let's say it's D modulo 7, the existence of D, and of course D is an element of G as well, so that we could really say, based on the result of the Keeley table, they're all element of G as well. Then A times the grouping B and C is also equal to the same value of D modulo 7. So since they are actually having the same result for usual multiplication, and the idea of multiplication modulo 7 is already presented here, hence we can say here that A star B star C is just equal to A star B star C. Because we already established that they are all elements of Z, and multiplication is associative in Z. Applying that to modulo 7, we have the same result. We're talking about this being equal to that, and since this is already equal to this, they're also equal to this portion here. and implementing the modulo 7, we have established that they are also equal. So hence, or therefore, star is associative in G. This is just my attempt in showing associativity, because if we're going to have, say, take note, we have 6 elements, right? Then we're going to use associativity here. So we have a lot of combinations to try, and it might take a lot of time. So I'm just talking about general perspective here. So we can say that G1 now is satisfied. So since G1 satisfied, let's proceed to G2. G2 talks about existence of an identity element. So let A be an element of G, any of those elements, 1, 2, 3, 4, 5, 6. We need to find E, which is still in G, such that A star E is equal to E star A will return to the value of A itself for all A element of G. This means that if we could guarantee a certain value of E that when subjected to A, that is already an element of G, we'll just return to A, and that E is still an element of G. This is true for all, okay, for all elements in G. That means E is our identity, and there exists identity element. If the identity element is not present, then basically we cannot guarantee that the set is a group. We can actually use here our KD table presented earlier. That's why we started with that. Okay, so let me copy this KD table. Okay, here, and just to have a reference. So the star was here, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6. Other references will just simply look at a specific column or row where the value do not change, talking about this and that here, and basically the item used or common to that would be the identity. Just for the purpose of discussion, let's illustrate that here. We can see that 1, when operated by 1, is just equal to 1, right? So 1 times 1, or 1 star 1, which is star the multiplication modulo of 7, is just equal to 1. As for 2 star 1, 2 star 1 is just 2, okay? But this is also equal to 1 star 2, okay? So 1 star 2. So we can see that if we are going to operate 2 to 1 or 1 to 2, the value of 2 will stand as it is still, okay? So you can see the pattern here that we have 3 star 1, again as mentioned for this column and for this row, is equal to 3, which is also true for 3 star 1. Similarly, 4 star 1 is equal to 4, which is also 1 star 4. 5 star 1 is just equal to 5, is also true to 1 star 5. And lastly, 6 star 1 is 6, is also 1 star 6. Looking into this, we know that this specific item is actually true for all. Okay, not just true for 1, but it's true for all. We can see that here. Sorry, red. I'm going to use red. Okay, we have here, it's true for all. This is also true for all. That's also true for all, right? So we can see here that this value, when operated to all the elements in our set G, the elements in set G will retain its value. So we can see here that E being equal to 1, being element of G, is the identity element for our star identified as multiplication modulo 5. Hence, G2 is satisfied. Okay, so G2 is satisfied now. Now, we will proceed to G3, and this time, I'll be using a different page for this. I'm also going to copy this KD table. Okay, going to that, because the third step or action rather for our group is the existence of inverse element for every element. Okay, so we'll have here G3, let A be an element of G. So we need to find the A inverse which are still in G, such that we can guarantee that A star A prime is equal to A prime star A will return to our E, which is just equal to 1, our identity element. That's why we started with G2 for this, because if we cannot guarantee the existence of identity element, then definitely we cannot move forward to existence of inverses for every element. Hence, it's not a group. So we have here something like this. To look that in our Cayley table, you can just simply encircle the identity element here 1. Here 1 is here. So you can see that for every row and every column, the identity element there is present. Hence, there is a pair for every row and column, for every pair of element that will result to our identity. The first one is for 1. Okay? When implemented with 1, will result to 1 in itself. Similarly, 1 star 1 is just equal to 1 in itself. This shows that 1, the inverse of 1 is just 1. Okay? Next, how about 2? What is to be paired with 2 that will result to 1? Similarly, that value must satisfy this, will also result to 1. Because if this is true, but this is not, then we cannot guarantee this. Definitely, we are going to stop and declare that the set is not a group. But for this, our 2 here is somewhere, the 1 is presented here, which is just a result of 2 star 4. 2 star 4 is 1. Let's look at the 4. 4, it's here, so it's still 4 star 2. So we can see that 2 star 4 is 1. 4 star 2 is also 1. This stands that the inverse of 2 is 4, and the inverse of 4 is 2. Because they both, when operated, both of them will result to 1. Okay, depending on the arrangement of the elements. So we are now done with the inverse of 4, because we're going to look at every element. Take note that the elements in G is 1, 2, 3, 4, 5, 6. We are down with 1, the inverse of 1, the inverse of 2, the inverse of 4. So let's look at the inverse of 3. What will be the element here or here when operated will result to 1. So the 1 of 3 is actually here, this portion. So it's actually the result of 3 star 5. So it's 3 star 5. Let's find out if 5 star 3 will be the same. Yes, 5 star 3 is also equal to 1. So with this now, we can say that the inverse of 3 is 5, and the inverse of 5 is also 3. So we have 5 elements already, or 5 inverses for the 5 elements. Now let's look at the last one. We don't need to repeat 4. We don't need to repeat 5. Let's look at 6. What will be the value here when operated to 6 will result to 1, or will be the same. So looking at this, 1 is here. So that's a result of 6 star 6. So 6 star 6, or this one here. So we can say that the inverse of 6 is just equal to 6 in itself. By the way, identification of inverses is very important, because as we move further for subgroups later on, the inverses should also be present in those specific subgroups together with the identity element. So with this now, looking at all of this, the inverses, or the results, or yes, the inverses for every element, 1, 4, 2, 5, 3, and 6 in the order presented here are still element of G, meaning they are still found in G. Therefore, G3 is satisfied. Because what you would like to see here is that we need to find A inverse for every A, but that A inverse should always be in G. What if in just one example, this is actually 8, the inverse of 6 is 8. So even if all the first 5 are found in G, but 8 is not found in G, that means that it's not satisfied. G3 is not satisfied. Just for the purpose of what if it so happened. So with G3, G2, G1 already satisfied. Here comes our conclusion that yes, we can say that therefore let me write G in this area for a better space. Okay, so G equal to 1, 2, 3, 4, 5, 6 is a group under your star, which is multiplication modulo 7. Okay, so that's clear now. That is really a group under multiplication modulo 7. This is again provided by this Cayley table. We start with that for easier identification, because in the first place, even in just this portion alone, identification of closure, if one element here is not but say it's 7. So you don't need to look at the axioms and declare that it's not a group. Okay? At the same time, this KD table was used for associativity. I mean, yes, the idea of existence of identity element and the inverses as well. Thank you very much for watching.